This is the second part of our sum score. We will focus on graph limit and flag algebra. It's our great honor to invite Andrzej Grzesik from Jagiellonian University, Poland. So let's welcome.
Thank you very much for the invitation. It's really a pleasure to be here and to see so many faces hoping to learn something new. Thank you all for coming. Yes, so we'll be talking about graph limits and flag algebra. So let me give you some motivation why exactly this topic. I assume that nobody of you know what graph limits are, or what a flag algebra method is. But you all know what are real numbers and what are rational numbers, right? So rational numbers are discrete, as graphs. So if I give you an easy problem, for example, minimize some polynomial in rational numbers, and I forbid you using real numbers. Now imagine that you have no idea what a real number is, you only know what a rational number, and I ask you to minimize such a polynomial, let's say in 0-1 interval. Yes, so if you think about it, then this is a really hard question. Why, if I allow myself to go into reals so that I have a nice smooth space, then it's really easy problem, right? Like now, if I go into reals, I can just calculate the derivative and compare it to 0, and then say that the minimum must be in some real number, which is 1/√3. Yeah, and going back to my original question for rationals, you would say that the answer is that the minimum is achieved by a sequence of rationals which are tending to this number. Right? You understand? Yeah, so this minimum, notice that this problem I formulated purely in rational numbers. I haven't used any reals in the formulation. But still, the minimum is achieved in some real place. So in order to have a solution in rationals, I would say that the solution, the minimum, is attained by some sequence of numbers converging to this. And in graphs, we have a similar situation. The space of graphs is discrete. It's like rational numbers. If you consider only graphs up to n vertices, then it's like considering rational numbers with some bounded denominator. And if you consider such rational numbers, you cannot do a tiny change. You cannot do like differentiating. Yeah, the same is with graphs. If you consider just some finite graphs on a finite number of vertices, you cannot do a small change, and you cannot do similar reasoning in the graph space. So that's why we would like to define some kind of a graph limits to make the space of graphs smooth, nice, so that I can do a tiny change, like differentiating, and I can obtain solutions to graph problems, like rational problems, using methods in graph limits, right? Here I moved from rational to reals so that I could be able to solve the problem. So similarly, if I have an extremal graph theory problem, I would like to move to graph limits, solve the problem there, and translate it to the graph solution. And flag algebras is one of the methods that are using those graph limits, that are working on graph limits, and the method gives us a way to solve extremal graph theory problems in an automatized way. So I can really take a graph theory problem, let's say, what is the maximum number of edges in inverted graph without graphons. This problem you know, I assume. What's the answer? You are shy. N squared over 4, right? And in a complete bipartite graph. So this is a typical extremal graph theory question. Of course, you can solve it without graph limits, but I will be solving it using graph limits to show you how one can use flag algebras, how one can use the method. And my goal is to get such a point that solving such a problem will be just pressing a button on the computer, and then the computer will generate a solution. So this is what I want to teach you during the next few days. Okay, are there some questions? In general, I'm happy to be interrupted. So if you have anything that you don't understand or you want to ask, or I made a mistake, that can happen, just ask. Like, you even don't need to raise your hand and wait if I see you or not, just shout. Like, really, I don't mind if you interrupt me with some question, or it's also better for both of us if you have some problem, something is not clear, then if you ask, I'm happy to explain. Okay, so let's move to graphing. In order to define these real numbers, I would need to define what it means that the sequence of rational numbers is convergent, and then what is this thingy that's a limit. Yeah, so similarly for graphs, I need to define two things. I need to define what it means that a sequence of graphs is converging, and then what is this thingy that could be its limit. In order to use flag algebras, I don't need the second part. It's enough for me to have notion of convergence, but I want to give you the graph limit theory a bit so that it will be more instructive and easier to understand. Okay, so let's try to define what it means that a sequence of graphs is converging. In order to do so, I need one more definition. I will say that the density of one graph in a different graph is the probability that, and the symbol I will mean always order of the graph age, so the number of vertices. So I choose this number of vertices at random from graph G, and I look at the probability that they create for my induced and so I pick vertices at random and look at the probability that they will really induce the graph that I want. So let's do some examples. Okay. Density of edges in a complete bipartite graph, K and N. Yeah, what it is? I pick two vertices at random, and I want to have that they create the edge. Picking two vertices at random, I need to have one vertex here, one vertex here, yeah, to obtain an edge. So what's the probability? You are so shy. I cannot believe that 70 people in the room cannot say what's the probability. Oh. Huh? Yeah, to be more precise, I could take out of side out of 2n vertices, I need to pick 2. And what are the good options for me? I need to have one vertex in the left part and one vertex in the right part. Yep. Okay. We can calculate it. It's almost. Okay. And we can do similar things. For example, if I want to calculate this, I want to emphasize in Ki, what's the densities of cherries in a complete graph? 0. Yeah. Yes, and this I want to emphasize that I'm not looking at just subgraphs, but induced subgraphs. So really, I need to find those vertices which are not connected. So it's impossible. That's why the probability is here. Okay. So you know the notion of density of one graph in a different graph. So now we move to the convergence. And I would say that the sequence of graphs here and I consider only graphs of growing orders. I'm not interested in a sequence of graphs where each graph in the sequence is the same triangle. I'm only interested in growing orders, like with those rational numbers. Interesting sequences for me that are defining nice real numbers are those where the denominators are tending to infinity. Growing orders. It's convergent if for every graph sequence densities in my sequence converges. Okay, so what it means? My sequence of graphs will be convergent if whatever graph I will choose and look at the sequence of the numbers, right? This is just sequence of numbers in 0, 1. This is just probability. And if this converges for every graph H, then I say that the sequence of graphs is convergent. Yep, clear? I need some reactions. Good. So let's see some examples. Let's say that my sequence of graphs is sequence of just these. Okay, then is it convergent or not? If I take any graph, let's say H, which is a complete graph, I will K5, then what is this sequence? At the beginning, it will be 0. There is no K5 in K2, in K3, K4. And from some moment, it will be 1. Yep. So it's a sequence which is just 0, 0, zeros, and then 1s, 1s, 1s. And it's clearly convergent. Where if I take as H any graph which contains a non-edge, then in this sequence, I have just zeros all the time. You're right? Okay. So if I have for every H a convergent sequence, then it means that this needs to be a convergent sequence of graphs. Easy? Okay, so let's do some different example. Let's say that I have Kn for even n and complement for odd. So this is my sequence. So is this convergent? If I take any graph H, let's say an edge, then what I have in this sequence of numbers? For even n, the density of edge in my sequence, which means in this one will be 1. while for odd n, it will be 0. Yeah, because the probability of finding an edge in a complement of a complete graph is 0. So this sequence of numbers is just 1, 0, 1, 0, 1, 0. It's obviously not convergent. And so this sequence cannot be convergent. It's enough to find one graph that is violating the condition. Okay, so let's do a different example. Let's say that Gn is your favorite planar graph on n vertices. So for every n, I ask one person in the room to pick favorite planar graph on n vertices. And this way I create it. Okay. You know what a planar graph is, right? So it's a graph that we can draw on the plane. Yes, so the question is this sequence of graphs convergent or not? So let's see, according to definition, as h, I will take just an edge. Okay, what's the density of edges in a planar graph on n vertices? How many edges can a planar graph have? Yeah, you know this Euler formula or something. Right? Number of edges in a planar graph is at most 6 and minus 3, right? Okay, so I have at most 6 and minus 3 edges. And in this definition, I'm dividing by number of all possibilities of choosing two vertices, right? So in order to calculate the density of edges in my sequence, this is at most 6 and minus 3 over n choose 2. Yeah, so this is tending to 0 with n. You're right? Yeah, this is like a larger order of magnitude. So whatever my graph is, the density of edges is tending to 0. So this will be a convergent sequence. And what about different graphs H? If you take any graph H which contains at least one edge, then I will have the same. The number of copies of this graph will be of lower order term than n to the power of number of vertices in the graph H. Yeah, so it will tend to 0. And if I take a graph which is empty graph, it does not contain any edges, then its density in any planar graph will tends to 1. Okay, which shows that the sequence of planar graphs is convergent independently of what choices of graphs I will take. In general, if I have a sequence of graphs so that its number of edges is subquadratic, so little of n squared, then it will be convergent. Yeah, with the same reasoning. So what I want to emphasize is that this notion of convergence is capturing only dense graphs. Yeah, whatever is not dense, whatever has less than quadratic number of edges will disappear. It will become 0. Okay, so this notion of graph limits of convergence is useful only for dense graphs. There are some notions of convergence for sparse graphs or some mixed setting. I will not cover it during this lecture. There was a school, I think, 2 years ago, and Jae-Hoon Kim was giving lectures on graph limits. So if you're interested, you can find it on IBS webpage, I think. Yep. What's 3 times?
The edge of a planar graph.
Ah, yes, you're right. You're right. I messed up the coefficients. That's true. Thank you. You got a point. Good. Yes, so I will be talking only about the dense graphs. If you're interested in convergence sequences and graph limits or in other settings, you can either check the lecture notes from previous school, or there is a nice book by Lovas called large networks, right? Or graphs, networks. And graph limits, right? Large networks and graph. By Lovas. Yeah, so the book is containing all notions of convergent sequences and graph limits. Okay. Some questions? There are no questions. Then let's move to the notion of the limit. And this is a harder part, but let's try to be slow and intuitive first. If I have a sequence of graphs, for example, let's say n, then I can associate with every graph adjacency matrix, right? You know what the adjacency matrix is. I have a matrix, and with on each place of the matrix, I'm putting 1 if the respective vertices are connected. So for matrix, adjacency matrix of a complete graph would have just zeros on the diagonal and everywhere else 1. Yep. And if I take bigger and bigger n, I will have more and more ones here. So if I ask you what do you think can be a limit, you would say that it's something like a square which is covered in ones everywhere. Yeah, intuitively. Okay, let's keep this intuition. And what could be the limit of k and n? So complete bipartite graph. If I look at adjacency matrix, it will have 2 parts. And inside part, I have everywhere 0. Yeah, here I have everywhere 0. While between the parts, I have everywhere 1s. You agree? So this is how the adjacency matrix is. Here is from 1 to n. And then it's continuing. So in the limit, I should also have something like a square, which is divided into 2 parts, 4 parts, with zeros here and 1s here. Okay, so now let's be more, where I have eraser. Be more precise. Graphon is measurable. So I make bigger or it's fine. Measurable function from 0, 1 square to 0, 1. Which is symmetric. And by symmetric, I mean that if I compute it in some x and y, I get the same value as in y. Okay, so what it is, it's a function which for every element of a square 0, 1 is giving me a number from 0, 1. So intuitively something like there. So I know that normally everybody are putting the originer here. Yeah, and if you look at 0, 1 square. But since I want to have analogy with this, I will put the origin here. Okay, so it will be square drawn from this point. with analogy to adjacent symmetries. Okay, so the graphon is just a function which is symmetric. Yeah, the value here is the same as value here. And goes to 0, 1. So somehow resembling the probability of finding an edge. Okay, and what you can think about it as just that this graphon is giving me probability between the vertices, where now vertices are like the 0, 1 interval. Like this is the intuition. Okay, I would like to define what it means density of a graph in a graphon. In order to do it, I need one more definition. Let me say a W random graph order n. So I have some graphon, I have such a function, and now I want to define what it means that I have a random graph of order n defined by this function. So intuitively, I'm choosing at random n points from 0, 1 interval. So n points here, symmetry here. And then between every 2 points, I look at the probability of having an edge between them. And by probability, I just mean the value of the graphon that's in this point. So let me be more precise. Such a graph is obtained by sampling n points in 0, 1 interval. Independently and uniformly at random. And as we said, I'm joining we say that those points are x1 up to x7. And joining I vertex with j vertex. With probability given by the graphon. So the value in xi is changed. Is it too low or it's still visible? I need some interaction. It's fine. Okay. So I hope you understand the concept. And having this, I define density of a graph in a graphon just by probability that W random graph of order number of vertices in H is isomorphic edge. Okay, let's digest the definitions. So what I do, if I want to find probability of, let's say, edges in my graphon, I'm looking at this W random graph of order 2. Yeah, so picking two vertices at random and looking at the probability that the two vertices are connected. And then saying that density of edges in the graphon is just the probability that I will see my graph as the random graph. So let's do some examples. Density of edges in this graphon. Yeah, I pick two vertices at random, and I look at the value that is on like defining the density of edges between them, the probability of an edge between them. And here it's 1. So wherever I choose the two vertices, they will be connected. Yeah, so probability that they create an edge is always 1. Say in this one, I need to pick two vertices at random. Yeah, and I'm interested in the event that they are connected. If I pick two vertices which are from the first half, they won't be connected. The value here will be 0. If I pick two vertices from the second half, they also not be connected. The value here is 0. Yeah, I need to pick one vertex from one part and one vertex from the other half. And this way they're always connected, and this event appears with probability half. And note that this is basically the same calculation as we did here, but without counting the exact error terms, because there is no n now. Now we have just full interval. Is it clear? Okay, so as an example, let's try to count cherries. Yeah, in order to find a cherry in this graphon, I need to have two vertices not connected. So they need to be chosen from the same part, either from the first half or from the second half, while the remaining vertex needs to be chosen in the opposite part. Yeah, we are right. So what's the probability that I will choose two vertices in one part? So this vertex can be chosen in 3 possible ways, and then I need to have probability half to be, no, let's see this way. I put this vertex anywhere, firstly, okay, and then I have probability half for each of the remaining vertices to be in the opposite part, right? So in total, I get 3/4 because I can find this vertex in this graph out of 3 possible ways. And then if I put it anywhere, for each of the remaining 2 vertices, I have half probability that they will be in the opposite part. If you calculate cherries in a KNN, you will see some formula involving n that will tend 3/4. For large n will be the same. Is it clear, or there are some questions? If one wants to be formal, then this density H in the graphon W can be expressed formally as an integration. So what I want to do, I need to choose at random vertices from 0, 1 interval, and I need to choose the number of them, which is in order of graph H. Okay, so this is this integration. Let's say that my variables are x1 up to xn, order of H. And then what I need, whenever I have an edge in the graphon, I need to look at the value between those two for every edge. So whenever x, I, and j I edge in my graph H, then I need to look at the value given by the coefficients, while for every non-edge, I look at the probability that they are not connected. Yeah, you agree? And there is an additional thing that I need to look at the isomorphic options. So I need to multiply this by order of H factorial divided by size of the automorphism.
For the cherry to be more, why is 3 for it?
Think about it this way. When I don't see a cherry, if I pick 3 vertices at random, all 3 needs to be on the same part, right? If they are not all 3 in the same part, then they are distributed 2 and 1. Okay? And when they are all 3 in one part, they are all 3 in first half with probability 1/8, and they are all 3 in the second part with probability 1/8. So in 1/4, they are in the same part, and in the remaining probability, they are distributed 1, 2. Yeah, like if you look at this formal definition, in the case of cherry, then this order of cherry is 3, so I have here 6, 3 factorial. The automorphism group is 2. I can just exchange those 2 vertices, the leaves cherry. So I get 6/2, which is 3. Yeah, which gives exactly this 3 here. And now this integration is just giving me quarter. It's just that I need to have 2 vertices from one part and the other from the third part, from the opposite part. Oh, yes. Yes, so the questions were already raised. Yes, all the time I'm talking about growing orders. That was one of the questions. Yeah, so order of my graph is all the time growing, so n goes to infinity. And as you noticed, I made a typo with 3n minus 6 as it's now. Yes, I'm not looking usually on the screen, so please tell me if you see a question. Okay, I think 40 minutes passed, and I think it's a good moment to have a short break. So let's make a 5 minutes break. And if you want, I will be here, so you can come and ask questions personally if you're afraid and shy to ask globally. So let's have a 5-minute break now. Okay, let's resume. As properly noted by the online tutors, I by mistake wrote factorial here. I mean just the size of the automorphism group, so the number of automorphism of H. Think about it, for example, if H is a complete graph, yeah, then every permutation of vertices is automorphism. So the size of the automorphism group is size of H factorial. It will disappear. Yeah, so yes, it should be just the size of the automorphism group without the factorial. Sorry for the mistake. Maybe I should say different. I'm doing all the mistakes intentionally, just to check if you are following correct. Find more mistakes. I challenge you. Okay. And now the important definition. I want to say that a graphon is a limit of a convergent sequence Yeah, we already know what a convergent sequence of graphs is. And now what it means that the graphon is a limit if for every H, so for every graph, these densities of H in my sequence, we already know from the definition that it converges, but I want them to converge to the density of H in the graphon. Yeah, so it's natural. We know that the sequence of graphs of growing orders is convergent if those densities converge. And I say that the graphon is its limit if they converge exactly to the numbers given by the graphon. Okay, and now when you think about it, it's highly not obvious that for every such graph, such sequence of graphs, there exists a graphon, yeah, because it's just one function from 0, 1 squared to 0, 1. And I have infinitely many graphs that I need to satisfy here. Yeah, so it's highly not obvious that for every sequence of graphs, every convergent sequence of graphs, there exists such a limit. Also, one can ask if every graphon is a limit of some convergent sequence of graphs. In other words, if we move back to the previous analogy, it's a question if every real number is a limit of some sequence of rationals, or we have some real numbers which are far away from the rationals, which would be strange, right? The same would be here. Like we would like to have that every graphon is a limit of convergent sequence, and also every convergent sequence gives us the graphon. Yes, as every convergent sequence of rationals is giving us some real number in the limit. Okay, so one question is easy. It's just some standard application of Azuma-Heffding inequality or some other concentration inequality. That if you consider those W random graph of order n, yeah, the thing that I defined there, if I consider those graphs, and then this is sequence of graphs, right? I have a graph for every n, and one can just check by those concentration inequalities that the density of such graphs, of any graph in such a sequence, is tending to the density of any graph in the graphon. Yeah, so in other words, indeed, every graphon is a limit of a convergent sequence of graphs. And this is easy. While the other inequality with the other direction is hard. And this was proven by Lovász and Szegedy. So let me write it formally. This is 2006. For every sequence graphs, graphs, there exists a graphon. Yeah, so thanks to this theorem of Lovász and Szegedy, we know that really for every sequence of convergent sequence of graphs, there is some graphon. One may ask if this graphon is unique. Yeah, like maybe there are more graphons that could be a limit of the same sequence. And indeed, that's the case. But maybe before I move to the uniqueness of the limit, let's see some examples. Let's do some graphs, some easy sequences. If I have a sequence of graphs, let's say, let's do the following graphs. It's got two parts. Each part is of size n½, and I have all edges in one part, no edges inside the other part, and let's say all edges between. So what could be the limit of such a sequence? Yes, something like a square, which is also divided into two parts in each dimension. And here, let's say that this is the first part. It will be fully connected, right? Between the parts, I have also all connections, and inside this part, I have nothing. Yep. Okay, what could be a sequence of graphs that were highly used in the previous lectures? So random graphs G and P. If for every n, for every two vertices, I pick an edge with probability P, where P is some number between 0 and 1. One can prove that this is a convergent sequence of graphs, using also some concentration inequalities. And what could be its limit? What do you expect? Yeah, in the limit, we need to have that basically between every two vertices, I have probability P. So it's exactly full square equals to P everywhere. Yeah, that's why in the definition of a graphon, which I think I already erased. Really? Yeah, here please constant. Yeah, so I'm not saying that the value needs to be 0 or 1. I'm saying it can be anything between. Yeah, so this is one of the examples. If I take a random graph, sequence of random graphs, then in the limit I obtain square, which is equal to P everywhere. Now, if you think about it, what's the W random graph of order n? This is exactly G and P, right? Because I'm taking n vertices at random and then looking at the probability of an edge between any 2 points given by this graphon. And this is exactly P for every choice. But I can have different graphons, right? I can have, for example, a graphon which has, let's say, more parts. And somewhere there are ones, somewhere there are zeros, and somewhere there are some probabilities. Yeah, there can be whatever. It may have even not the structure like of a grid, it can have a different one. It needs to be symmetric. For example, I can have a graphon which looks like this. And now it will be your task to think what could be the sequence of graphs which tends to such a graphon. Or let's say this. Oh, by this I mean here are ones. Those are ones, the remaining 0. What could be the sequence of graphs which is converging to such a graphon? I will leave it as exercises so that you can think about it, and we can discuss the exercises later. Or maybe let's do one more example. Let's say I have 1 here and this is 1/3. Can you tell me what could be a sequence of graphs which is converging to such a graphon? I'm so shy. I need some interaction. What could it be? Yeah, on the first n/3 vertices, I need to have all connections. Yeah, so it's like a clique. On the remaining 2/3 of the vertices, I also need to have all the connections. So it's like a bigger clique. This is on 2n/3 vertices. This is on n/3 vertices. And between, I have zeros, so I don't put any edges. Yeah, so it's a sequence of graphs where each graph in a sequence is just a union of 2 cliques, where one clique is 2 times bigger than the smaller clique. Yeah, I hope you understand. Good. Okay, so thanks to Lovas and Szegedi, we know that for every convergence sequence, we have a limiting graphon. We know that every graphon is a limit of a convergence sequence. So let's think if this limit is unique. Okay, so if it's possible that I have a sequence of convergence sequence of graphs, and I could have 2 graphons that appear as its limits. And the answer is yes, it's possible. So let me do an example. If I take complete bipartite graphs, sequence of complete balanced bipartite graphs, they converge to a graphon which looks like this. Yeah, we agree with that. But what if I take a graphon which is not divided into 2, but into 4, and I put ones as in chessboard. How this looks like. I have 4 groups of vertices. Yeah, intuitively. Let's see, 1, 2, 3, 4. And from inside, there are no edges. Between 1 and 2, I have all possible edges. Between 1 and 4, I have all possible edges. Between 2 and 1, 2 and 3. Here is between 3 and 2. It's already 3 and 4. So what's the graph? Yeah, it's also complete bipartite graph. If I just consider those 2 as my parts, then this is complete bipartite graph. And so you see that basically this graphon and this graphon is basically the same. So if I calculate all those densities, so I calculate density of H in the graphon, this or that, it will be the same. So in particular, both those graphons are limits of the same sequences. But they are somehow similar. Yeah, like if you think about it, then this is just something like reshuffling the vertices, like permuting the vertices of a graph. If I exchange this group with this group, similarly here, I will obtain this thing. And it's clear that this can be done in general. So if I have any measure preserving from 0, 1 to 0. By measure preserving, I mean that the measure of the pre-image is the same as the measure of the set. And I can define a graphon after the transformation of this measure preserving map, just by putting value of this graphon as value after the function. Yeah, so I take some measure preserving map. You can think about it as just reshuffling the vertices. And then I say my new graphon in X and Y is exactly the former graphon taken in the values after reshuffling. Okay? So with this, you can see that I can define a measure preserving map here, which will reshuffle this guy into this guy. What can be proven if I take any such a measure preserving map, so any reshuffling, then this graphon and this W with measure after reshuffling will give me exactly the same densities as the original graph. So let me say that 2 graphons are weakly isomorphic. Density of any graph in one graphon is the same as density of this graph in the other graphon. Okay, in other words, 2 graphons are weakly isomorphic if they are limits of the same graph sequences. Yeah, because the densities of every graph in each of the graphon are the same. And now comes the nice theorem by Borg's change in logos. The graphons W are weakly isomorphic. So they are limits of the same convergent graph sequences if there exists measure preserving maps. Zero, 0, 1. Such that if I transform first graphon to the first map, I obtain the second graphon transform with the second map almost everywhere. Yeah, I hope it's clear. So I say that two graphons are weakly. The theorem says that two graphons are weakly isomorphic, so they are limits of the same graph sequences if I can transform each of them by some measure preserving maps into the same graphons. The same almost everywhere, because of course if I change some tiny fraction here, then it will not influence the density. Okay, so almost everywhere are the same. Is it clear? It's not easy to see, but this can be proven that a similar theorem with just transforming one graphon into other is not true. I really can have two graphons so that I cannot transform one into another by measure preserving map, but I can each of them transform to the same. That's why I need to have two maps which are transforming the graphon into the same graphon. Almost everywhere. Everywhere. Almost everywhere. So think about, for example, that I have this graphon and I change its value in one place. Okay, for this particular here and here, keep it symmetric. So for some particular value, I change one single entry. Then it's not influencing those densities at all. Yeah, because probability that I will choose exactly this value is small, it's 0. Yeah, that's why I can consider graphons up to tiny changes, like measure 0 changes. Yeah, so this graphon with the changes is, formally speaking, not the same as 0, 1. Yeah, because there is a difference. But I will say that they are equal almost everywhere. So everywhere except some measure 0. Some more questions? Okay, so if we wrap up everything that we learned today, what do we have? We know what it means that a sequence of graphs is convergent. Sequence of graphs of growing orders is convergent. And we know that if I have such a convergent sequence of graphs, I can find its limit, its graphon. I know it's unique up to some kind of reshuffling. And I know that every graphon is a limit of a convergent sequence. Yeah, so basically, going back to the previous analogy, it's something like proving that every real number is a limit of a convergent sequence of rationals. The limit is unique somehow, and there is no real numbers that are far away from the rationals. Like really, every is a limit of a convergent sequence of rationals. Yep, you feel the theory? Okay. I haven't proved those theorems. Skip it. I think it's not giving you too much insight to see the formal proofs with all the integrals and everything. But if you're interested, you can go to the Lova's book. And as I said earlier, there are many other notions of sparse graph convergence or some mixed settings, but it won't be needed for our for the method I'm planning to teach you next days. Some questions? No, I have still some time, so let me do one more thing. We would like to say what it means that two graphons are close to each other. What it means that they are close. And in order to do so, I want to define some metric on the space of graphons. But before it, I need to generalize the graphons a bit. So let me say what the kernel is. Kernel is a symmetric measurable function from 0, 1 squared. So what's the difference between a kernel and a graphon? The difference is that in a graphon, I was assuming that the values are between 0 and 1, because they were representing the probabilities of edges. And here I'm not restricting it. Yeah, kernel can have any real values. And in such a space of kernels, I'm defining a norm. This is called cut norm. And it's denoted by a small square. So intuitively, I'm looking at graphon or kernel, and I want to find some set of vertices, so that the value on the cut is as big as possible. I think this is not perfectly clear. And I look at the value of the cut between. And so I take a supremum over all such cuts, so all subsets of 0, 1, and I take the integral of the values of the cuts. So formally, one can easily prove that this is indeed norm. So it satisfies all the conditions that we want from a norm. And this defines a metric. It's called cut metric between two kernels just as a cut norm of their difference. So this is the point where I needed to go into kernels from graphons. And so if I take two graphons, I look at their difference. So now it can be minus one even in some places. And for the difference, I use this cut norm to calculate it. To calculate the cut norm. And if cut norm is big, it means that they are far away from each other. You can think about it. Say I have one graphon which is complete bipartite, the other one which is full sleek. In some parts they are the same. Yeah, if I cut, for example, first half and second half, like between I have all possible edges here and all possible edges here. But if I consider different cuts, for example, like first quarter to the second quarter, then here there are no edges, while here I have a lot. Yeah, this shows me that they are quite far away. Yeah, so this notion is capturing if they are far away from each other. No, unfortunately, this notion is not capturing the difference between such two. Yeah, I still need to consider this reshuffling. If I look at this graphon and this graphon, and I just plug in the definition of the cut metric, then their difference will be high. And so because of this, I need to do here one more thing. I need to consider all possible measure preserving transformations. So let me say that S01 is a set of all invertible measure preserving maps. Zero 1 to 0 1, that's all the time considering. And let me define also S bar as the same, but without invertible. So just set of all measure preserving maps from 0 1 to 0 1. And now I want to define cut distance between two graphons or two kernels. And this is denoted by delta with a square. As looking at this density, the cut metric between U and any reshuffling of the other one. And I want to find the best one. Okay. So, in other words, I want to know how far graphons U and W are. And I say that I look at this cut metric, so how far they are, but not between U and W, but between U and any possible reshuffling of W. Okay, here I look at only invertible, but what one can prove is that this is exactly the same as if I look on all the reshufflings. And it's also the same if I look at reshuffle of just the first one. So it doesn't matter if I'm reshuffling the first one or the second one. And it also doesn't matter if I reshuffle both of them. So Sorry that it's quite small. It should start higher. Okay, but what I want to say is that it doesn't matter if I'm reshuffling just U, just W, or both of them, or if I'm reshuffling only using measure preserving maps which are invertible, or all of them, it's always the infimum is the same. Okay, so after all those possible reshufflings, I find the infimum, so the one that is giving me the smallest cut metric, and this is my cut distance. Yeah, in particular, if I take those two that we considered earlier, I can reshuffle one of them to get exactly the other one, and the cut metric will be 0. So the cut distance between them is also 0. Yes. Yes. The importance theorem is force times Mr. Gombi. Okay. Is saying that two graphons U and W are weakly isomorphic. Yeah, which means that there are limits of the same convergent graph sequences if and only if the cut distance between them is 0. Yeah, so basically this cut distance is exactly capturing what we want. Yeah, whenever the cut distance between two graphons is 0, it means that they are weakly isomorphic, so they are limits of the same graph sequences. While if it's not 0, then they cannot be weakly isomorphic. So what we can do now, we can think about all graphons. Let me use the notation of Lovász. I look at all graphons. Where weakly isomorphic graphons are identified. Yeah, so I consider all weakly isomorphic graphons, so all the ones that have cut distance 0 as the same. Yeah, and now I look at such a space. So this is called unlabeled graphons. You can think about it as an equivalence of unlabeled graphs, right? In a graph, we take a look which vertices are connected, but if we consider all possible permutations of vertices, we get unlabeled graph. Yeah, so here is similar. I look at all possible graphons, but I identify those that can be obtained by some reshuffling. So all the ones that are at cut distance 0. I get unlabeled graphons. And the important theorem of Lovász-Szegedy from 2007 is that the space unlabeled graphons with metric defined by shot distance is compacted. Yeah, what does it mean? It means that if I have a sequence of graphons, then it needs to contain a convergent subsequence. And so this space is really nice. This sounds like, okay, shortly speaking, we define some nice space of graphons. Yes, like using this previous analogy, we defined real numbers. And it occurred that the space that we have just defined is really nice. It's a compact space. Yeah, so now we can use all of the analytic tools that we know for compact spaces and lots of other analytic ideas. Okay, I think it's a good moment to stop. So let me stop here. And if there are any questions, I'm happy to answer.